Here we're given a function f of x is equal to x squared, and g of x is equal to some transformations of f of x. We're asked to find an equation to represent g of x, it's this function, and graph both f and g of x. Well, to find g of x, we are going to algebraically substitute the function f, given here, into its place in the function notation. So I'm going to write the outside parameter, as usual, but instead of writing f of negative x minus 2, I'm going to substitute negative x minus 2 into this x squared function. So negative x minus 2 squared. That takes all of this function notation and places it as input into any occurrence of x in the function. Well, now what we can do is we can simplify this a little bit. I could just graph it, but this negative here is really not going to matter because, as we recall, our exponent laws tell us that everything inside the brackets, all two terms, the negative 1 and the x minus 2, must have this exponent raised to them. We know when we raise a negative to a power that's even, we create a positive. So that negative is simply going to disappear. And I now have a simplified function for g of x. G of x is equal to 1/2 x minus 2 squared. So the first thing I'm going to do is graph f of x, because it asked me to graph f of x. Now remember, f of x is our base parabola, so we know its vertex is at 0, 0. Then we go over 1, over 1, up 3. And we use symmetry to find the points on the other side. So this would be, and continuing on, our function f of x. And we have these key points here. Now this is really nice because it explains why that negative is redundant. In g of x's original definition, there was a reflection in the y-axis of negative 1. Well, if I take this function and reflect it, this arm just becomes this arm. And this arm just becomes this arm. So the reflection really doesn't mean anything. Now we'll apply the parameters that we have here. So this parameter is outside of the squared portion of the function. So we have an a parameter equal to 1/2, which means we're going to have a vertical compression. And inside the function, we have a c parameter equal to 2. Remember, it's opposite of what you think. So we're going to be moving this thing to the right 2. Notice I grabbed the parameters from the function g of x, but I could have also grabbed it from its definition and function notation. Here we see the half is out front, and we see negative 2, so opposite of what we expect in the brackets. So we'll apply the half to each of these values. I'll do the first part in pen, and then I'll do the last part in green. So each value here gets moved to half its distance from the x-axis. And now all I have to do is translate every single point right 2. So starting with this point, I'll go right 2 to there. Going from this point, I'll go right 2, and it's actually going to create this point. Going from the vertex, which stayed there, right 2, I'll have my new vertex here. And now I can use symmetry. There's the axis of symmetry through here, so I know that this point would have been translated to there, and then this point moves to the right 2. Notice it's symmetrical about the axis of symmetry. And this is my new function, g of x.